Kinematics in two dimension. In the last chapter, we talk about motion of an object along straight lines or one dimension. In this chapter, we uh, talking about objects move on two dimensions. We're going to add another dimension in this chapter. So, for example, uh, it can be a plane, motion of objects on a plane. Plane means it has two dimensions. It can be x and y or x and z, which is like a vertical plane or horizontal plane or any inclined plane. So any movement or any motion of objects in two dimension or planes fall under this category. In one dimension motion, we use letter x to represent motion along x direction or any linear direction. In this chapter, we use a special letter R, which represents, in this example, x and y, which is a plane. Any motion along this plane, we can use R. So for example, not always we consider as the initial position. So this initial position, you see, it has motion along x direction and also motion along y direction. But with respect to initial position, your final position is here. So displacement is a vector. So therefore, it only related to final position and initial position. Therefore, it doesn't matter you travel x direction or you travel y direction, as far as you know the initial location and final location, you can find your displacement, which is a vector which related to initial position and final position. And also the second vector r, this is the final location of this car, and that location, the displacement is like this, and it has again x direction and y direction. So in this example, your displacement delta r, change of r, your initial position is here, your final position is here, and delta r is this. It all depends on initial and final position. So delta r is equal to final position and initial position, and if you take the difference, you get the displacement along 3D plane. Now we can define velocity of an object on two-dimension plane. So in the previous chapter, we defined velocity along a straight line, which is displacement along x direction, final minus initial, and final time minus initial time, time difference, position change, and the time change, delta x over delta t. Similarly, we can write position change along xy plane, which is r. No, r is your final position, which is this location, and your initial position in xy plane, this is this. So del r minus r naught is delta r. This is the vector. It's related to final position and initial position, and the direction is from initial position towards final position. And delta r over delta t is velocity of an object on two-dimension plane. In the previous chapter, we talked about instantaneous speed or velocity. Speed or velocity of an object at a given time, at a given location. It's a very small time interval, And in your equation you see limit delta t tends to 0. Delta t means the time interval tends to 0, goes to 0 means it's not 0 but very, very small. So very, very small time interval means it's an instant, very short period of time. You can talk about a velocity, and because of the small interval, which means it's a specific location, therefore we call it instantaneous velocity. We can define the acceleration like the last section. Acceleration is velocity change divided by the time change. So delta V over delta t. So with the acceleration and the velocity for two dimension, we learned in the previous slide, we can write four equations very similar to the four equations we learned in a previous chapter. These are the four equations we learned for motion of an object in one dimension. Final velocity is equal to initial velocity plus acceleration times time. Final velocity square is equal to initial velocity square plus 2 times acceleration times final position. And also final position is equal to initial velocity times time plus half acceleration times t square. With these four equations, we can make 8 equations. 2 equations for each linear equation or one dimension equation. So we can write 2 equations, one along x direction, one along y direction, and the two-dimension equation has a small change. You will see in the next slide. So this is one dimension, and when you go to two dimension, we talk about x direction and also y direction. Therefore, we have to put some subscripts so that when you see an equation, you can tell it is you write that equation along x direction or y direction. Here is an equation of motion along x direction. Along x direction. So only difference is you see subscript x for velocities: initial velocity, final velocity, and acceleration. Initial velocity, acceleration, and final velocity, initial velocity. So everywhere you see x. This x means the equations, motion, there's equations, kinematic equations we wrote in first chapter. We still can use it with the subscript x, which means this is for x direction. And we can write 4 different equations for vertical motion. If an object goes up or down, we can write a equation with a y, letter y, which represents that equation we specifically write for y direction. In this slide, you see a picture, a plane on a vertical plane. So therefore, it's y direction. It can go up or down. And for this motion, to learn about the speed along y direction, how fast it's moving up or down, or what is the location in y direction, we can use these equations. And these 4 equations similar to the equations we wrote for horizontal direction. In this case, we put subscript y for each equation, which represents this equation we specifically wrote for motion, describe the motion along y direction. So the meaning is same, the position along y direction. The previous equation has position along x direction, therefore we put x, and v naught is we know initial velocity, and we put another y, which means initial velocity along y direction times time plus half acceleration along y direction. We talk about free falling objects if there is no uh, air resistance. This acceleration, vertical acceleration, we call it acceleration due to gravity, and you always can use these equations for objects without air resistance as 9.8 meters per second square. So acceleration, you always use the vertical acceleration due to gravity, which is g 9.8 meters per second square. So any vertical motion of object, you always can use this acceleration, and you can calculate the speed along y direction, final or initial, and also the final position using any of these equations. Let me move to slide number 18. Equations. So in this case, you see here acceleration along y direction is negative 9.8 meters. We know acceleration is a vector, so negative means it's in this direction, and we always consider horizontal x direction, positive direction as this, and positive y direction is upward like this. And therefore, if the acceleration is pointing downwards, you have a negative 9.8. It represents the direction. And let me write, this is one of the equations we learn to calculate the speed or velocity along y direction. Final velocity is equal to initial velocity along y direction times plus acceleration along y times t. So since we already know the acceleration along horizontal direction, instead of ay, you can write negative 9.8. And under the influence of gravity alone, an object near the Earth's surface will accelerate. So if there is no air resistance, you can consider there is no acceleration along x direction. So therefore this term becomes 0. So your final speed along x direction of an object under influence of gravity, there is no acceleration, and therefore his x speed before or after is same, remains same, because there is no acceleration.